All right, chapter 2 goes into talking about limits of a function. Got the definition 2.3 up on screen here, and I'm just going to read through it and kind of give you a little feel for what's actually happening. It's a bit wordy. The succinct version is probably the best way to go, but I want to at least mention a few of the things in the definition. So the definition says, let f of x be a function defined at all values in an open interval containing a, with the possible exception of a itself. So essentially what that means is x has to be defined everywhere in an open interval, but at potentially at one different spot. So there's examples down below where I'm kind of showing you where it's not, or the book is showing you where it's not actually. It doesn't actually exist or is not defined in those values. The next part, if all values of the function of f(x) approach the real number L. So this has got to be some number L. So that's your f of x essentially. As the values of x that aren't equal to a approach the number a. So basically what it says is as we get closer and closer and closer to the value x that is a, we're getting closer and closer, stays close to some value f of x, which is L. And if that's occurring, we say that the limit of f of x as x approaches a is L, and that's the wording of it. So the succinct version, I've already kind of mentioned it. As x gets closer to a, f of x gets closer and stays close to L. And this is the notation we would use. Limit, and the underscore there, or the subscript under there is x with an arrow a. That means x approaches a. Of f of x, which is our function, equals some real number L. So there's three different graphs below that deal with three different functions, and we're looking at the limit at x equals 2 in each case. So the first one, a, you can see it's just a straight line with a hole where x equals 2. And again, that hole illustrates that there isn't a value there. It's not defined. And given the function below, the reason is in our denominator we have x minus 2. That means if we put in 2 for x, we have a problem. We can't have a 0 in the denominator, and that's why we're showing a hole. Well, according to our definition, the fact that x doesn't exist at 2 isn't that big of a deal. In this case, we're looking from the left. The values getting closer and closer and closer and closer to the real number 4. So the y value is 4 as x gets closer and closer to 2. From the left-hand side, from the positive direction, we have the same thing. As it gets closer and closer and closer to 2, we're getting closer and closer to 4. Thus here, the limit as x approaches 2 for this equals 4. That satisfies our definition. Now the other two do not. Here's the problem. So coming from the right-hand side, from the positive side, we get closer, as we get closer and closer and closer to 2, we're staying at 1. So we're not deviating from 1, we're not getting any further away, so that seems to work. However, coming from the left-hand side, from the negatives, we're at -1 the whole time, and we have this gap. This gap here. So we'll talk about one-sided limits later on, but as it stands, we're not getting closer and closer to one number from all sides. So this has no limit. So limit as x approaches 2 of f of x does not exist for this one. Okay. In a similar fashion, we have values going up to infinity from both the positive and negative side. Now, according to our definition, here the limit as x approaches 2 of f of x also does not exist. Now, we're going to show notation later on where we're going to illustrate this as being infinity, because in both cases it does go to infinity. But according to the strict definition of the limit, there is no limit for graph C as well.